Yeah, hi everyone. This video will be talk about the transient flow for the groundwater model. So the previous video, I talked about the Laplace equations and how to solve it. And this video, I will talk presents more about the transient flow in here, and conditions for this case will be the horizontal flow in the homogeneous with isotropic in confined aquifer for the constant thickness. Yeah, and try to solve it. And in here I have already rewrite these equations like this. And this one I just consider for the two dimensions. So that's why I just have the y's, the x and y directions in here. And for the transients, I also have the potential of s over potential of t time multiplied with s, the storage coefficients here. And in here the initial conditions, I consider I have the Ts equal Ty and the delta x equal delta y. It makes the equations more simple. Okay, in here just rewrite the equation. We will have the form like this. So in here you just look at the potential of t in like this. So the n's positions in here is present the positions, the change of the t variable in here, and i's will be present for the x directions, and j present for the y directions. And in here you just have the potential of t in here. So that's reason why the i's and j for your x variable do not change anything, do not plus or minus 1 anymore. You just have the n's plus 1 in here and n's in here, because it's just follow the t variable. And this one you have the t over delta s square, because you apply the finite difference methods, and you will have this kind of the formats. And in here you can see in here, because in here we consider the x directions and y directions. So that's reason why you have the I and j changes like this. You have the j plus 1, j minus 1 is present for the y directions, and I minus 1 and I plus 1 just present for the x directions. And you have the center point in here, Sij, and look at the n's positions, and just keep the n's minus 1, all of this, because in here you you just consider the x and y direction. You do not consider the t, change the t variable. So that's reason why your n's plus 1 in here just keep in these positions, do not change. And why you have the n's plus 1 and n's in here, so it's too easy to understand that. You just picture in your mind as the n's plus 1 will be the future of the n's, because in the transient flow in the beginning you will have the the value of s, I, j as the positions of n, and the s of I, j at the positions of n's plus 1 it will be the future value you will have. So it's just easy to understand. You just think that the s as n plus 1 is the future point of s as n. Just this. Yeah, and in here you just rearrange the equations, and you have this kind of form. This one you just put the delta s square in here, transfer it to this, t from here to here, and you have this form like this. And in here you just this term will just disappear, and you just have this one in here. And from here, why you have the minus here? Because in here, just look at this, you have the Sij in here, and on the right term you also have the Sij in here with the coefficients of the minus 4. So I just want to combine the coefficients of this, the minus 4, and the coefficients of this Sij, this term. Just want to combine the coefficients of Sij. So that's the reason why I just put the Sij from the left term to the right term, and I have the coefficients of Hij in here. You have the minus 4 here, and the term of s, delta s over delta s squared like this. Just put in here. So that's the reason why I just have the minus here, because in here I just have the minus delta s square of Sij at n, and the Sij of n plus 1 I just put in here, because this one also have the same Sij of minus of the n plus 1, and this one is the Sij of n plus 1. So that's the reason why I have the coefficients term like this. And from here I just set up the m equal s multiply with the delta s square over t times delta t, and I just put the substitute, right, replace the m from the coefficients of Sij and in here like this. So I have the final equation like this, and rewrite it like this. So that's the way to solve the transient flow. So the next step, like the Laplace equations I solved in the previous video, we have to build a system equations and build your matrix, and finally just solve it, and you have the variable you want, the x variable, the unknown you want to find. And the way to solve it is just the same with the Laplace equations. The difference here is just the coefficient in your the coefficients runs out, the variable will be changes. So for example, I have the grip. It's the same with the grip I use for the Laplace equations video. I solved it before. So I have the grip like this. So instead of I use it for the steady state flow. So in this case, I just use it for the transient flow. And this one is the way to build a system equations. It's the same with the Laplace equation. The difference is just it's just the coefficients runs of the equations, and it's just used for the interior nodes like this. The node, the points lie inside the grid, right? So instead of in here you have the interior nodes, you have to use the Laplace equations like this. So in the situations of the transient flow, you just use the interior node for these equations. For example, I have the S22 like this. S22 like this. So this one is for the Laplace equations. But for the transient flow, I have the okay, just again, for the transient flow, I have the minus for coefficient, the Laplace equation. I have the Laplace equations for the steady state. I have the minus for in the center node like this. I just because this kind of form, I have the minus 4 in here. But in the transient flow, I will have the minus 4 plus m for the center node, and the B column, instead of the zero value, I have the m multiply with the x I j of n. So in these situations, minus m multiply s I j of n is the null value, and minus 4 of n is also the null value. So all of the parameter in here, the m is have the s, delta x, t, and delta t. You already know the value of this, of all of the parameter. Yeah, so it's just the constant value. You already know. You just replace on your equations, and you have the a form, a particular form for your measures. Yeah, and this one is the measures for the Laplace equations. But for the transient flow, you just instead of you have the minus 4 in here. So for the transient flow, you will have the minus 4 plus m, right here. The center point, you have the coefficients of minus of 4 plus m like this, for your center point. And the routing point, the point all around your center point, have the coefficients of 1, so it's the same, right here. And with the B column, instead of the zero value here, you will put the minus. Just remove the zero. So your B column here, you have the minus m multiply with s I j at n positions, at n value. Yeah, and all of the boundary is the same. The way to calculate the points on your boundary, on your no follow boundary and your here the nodes in here for the no flow boundary and for the specific boundary it's the same with the Laplace equations for the steady state. The difference is just you just change the way to solve the inside point here, interior point in here. Your chat is the difference, and one small difference. So the pupil asked me that how about the Sij n? How can we know that? So in the beginning we will consider Sij Sn will be equal 0. So Sij n will be here. This one is B vector, right? So the Jensen's flow is mean you have a lot of scenario, right? A lot of model, a lot of scenario. Because the Jensen's flow, you have the groundwater heads. The groundwater heads will be changed over time. So it means you have a lot of scenario, a lot of model, a lot of steady state model, transient, right? So it means that in the beginning for solving the transient flow, you just consider the Snj equal 0. And it will be put on the B column in here. Here you have the n already. You just consider the Sij equal 0 in the beginning, and you put the value, all of the value in the B column in here, and calculate and find the x value in here. So that's the case for the beginning. How about the next one? The next one, when you have the variable of s, in this case you just put the x you have in here, put in here. You just put the all of s you have here in this, in the B column, and try to repeat the calculations until you have the final scenario for your transient flow. So that's the way to calculate that. For example, you have your transient flow have transients from the beginning, the first day, to the 30 day. It means you have the 30 scenario, right? So it means you have 30 x Ijn. You just have the variable in here, the variable of x in here, and put it in here. Okay, again, in the beginning, the first day, you just consider the xn in here, x of Ijsn equal 0, and you put it in here. And when you solve this matrix, you have your new variable of s in here, and you continuous put your s variable you already have in here in the B column, and continue calculate your model, and the process will be repeats over and over. So for example, you just have the transient for the 30 days. It means you have to repeat it 30 times like this. and you got the s variable in the ends, and you just put all of the result of s, all of the result of your simulations of your groundwater model, and you will have the final result for the transient flow. So that's the way to solve it. Yeah, thank you for watching.